Thank you very much, Frank. Thanks to all three organizers for giving me the opportunity to give this talk today. Um, I was told to make this to go gentle on these algebraic geometers in the audience. No worries. There's very little differential geometry actually happening today. I will like the background I will assume is well like some I will talk about differential geometry in a way that algebraic geometers should like find conducive. So there's going to be ring spaces. There's going to be quasi-coherent sheaves. I think these are maybe things that are close to your hearts. And I'm going to assume some prerequisites in homotopy theory and higher category theory. So I'll talk sort of fairly informally about infinity categories and just assume that sort of we're all on board with this. Okay. So six operations, this refers to six-functor formalism. So let me just briefly flash for you what those are. Let's see if we can get this to work. There we go. So a six-functor formalism, in this day and age, you should start with some category or an infinity category that you think of as containing geometric objects of some kind. And you suppose that this category has finite limits, which means you can intersect these objects. And what a six-functor formalism does is it assigns to each such objects another infinity category. Usually it has some kind of linear flavor. Maybe it's stable or it's enriched over vector spaces or something like that. And there's a bunch of functorialities this comes with. So for a map between objects in this category C, you have a pair of adjoint functors, f upper star and f lower star, which usually are just called pullback and push forward. Just think of sort of maybe C is like the category of topological spaces, and D of X is maybe sheaves of Z modules or sheaves of spectra, and then you have the usual operations of pushing forward and pulling back sheaves. But also, if you're working with at least with locally compact Hausdorff spaces, there are further operations that at least exist on the homological or infinity categorical level. For a map, you also have two other adjoint functors, f lower star and f upper shriek. And the thing to notice that sort of the variance of this adjunction is reversed with respect to the star adjunction. So f upper star goes from dy to dx, and here f upper shriek goes from dy to dx. And so here above here f upper star, that's the left adjoint, but here f upper shriek is the right adjoint. And then also one requires all of these categories to be symmetric monoidal. And not just that, they have to be closed symmetric monoidal. So you can form inner homes with respect to this tensor product. And here we see the six functors. So can everyone see so if I like move this cursor around, people can see this, right? Okay, great. So this is two functors, f upper star, f lower star. Two, the shriek functors, that's another pair of functors. So here we have four, and then the tensor product is another functor. And then its adjoint, the internal hum, is the sixth functor. So those are the six functors. And this is just a start. So this comes with a lot of sort of infinite list of coherence data. So first of all these functors should be monoidal, lax monoidal. And here's the important one. So whenever you give yourself an intersection, a pullback square in this category, part of the data of a six-functor formalism is an equivalence between the two ways of going around the diagram, where say you start with Z. First, you can apply H upper star and then F lower shriek. Or you can apply K lower shriek and G upper star, and you require that there is an equivalence between these two functors. That's a piece of data. That's not a priori given to you. The other important thing is that sort of if you have a map from X to Y, then the star functor gives you an action of the category dy on the category dx. And what is required is that the lower shriek functor is linear for this action of upper star. And this linearity is encoded by this equation, which is known as the projection formula. And this is actually just the beginning of a series of a long list of coherences, right? Because if you take two pullback squares, you can put them together and get a new pullback square. And sort of there's a Bayesian equivalence for each of these three pullback squares, like the two you get and the two that you compose, and those have to be compatible as well. So it's a higher piece of sort of a two categorical piece of datum, and then maybe if you compose three pullback squares, there's a three categorical homotopy that's mediating that all ways of composing are the same, and this just keeps going on forever because we're doing homotopy theory. We're dealing with higher categories. So this might all be hard to formalize, and so I should mention also what one usually requires that this assignment is local on C. So usually we think of C as like some notion of spaces. There is a natural topology on this category, and we require that this assignment D is a sheaf for this topology. So the upper star functor should make D into a sheaf. Okay. So it turns out nowadays that all of this data is very conveniently encoded as a single lax monoidal functor from the categories of spans of C into the category of categories, or the category of infinity categories. And so the category of spans of C, it has the same objects as C, but its morphisms are little spans. And composing spans is done by pullbacks. And these pullbacks the fact that this is a functor and the morphisms of spans are pullbacks, that is going to encode for you this base change property, for instance. So such a functor is just a three functor formalism. So this encodes the upper star, the lower shriek, and the tensor product, right? So if you have a span, then the right functor or the left functor, depending on how you're looking, is the upper star, and the right functor is the lower shriek. And you get a six-functor formalism by just requiring that all these functors have adjoints, right? That's what we saw on the first slide. The other functors are just the adjoints of these three functors. And so to guarantee this and to be in a setting where we can easily deduce that adjoints exists, we're gonna slightly tweak this. So actually, instead of the category of categories, we're gonna work in the subcategory of so-called presentable categories. And here the morphisms are required to have left adjoints. So this is a very nice sort of this setting of presentable categories is a very nice place to do category theory, to do algebra with category theory. And so, for instance, in particular in this setting, it's very easy to deduce that certain functors have adjoints by just checking that that functors preserve colimits. So there is a plethora of six-functor formalisms, and like I could tell you now, sort of these are they're how this formalism encodes all the functorialities that cohomology theories enjoy. These give you powerful categorical invariants in motivic homotopy theory, étale homotopy theory. They can be used to define topological quantum field theories. Explaining this will take me far away, so I want to focus on a particular one right now, a new one in differential geometry, and then at the end of the talk, I will just tell you for this specific six-functor formalism that I'm going to construct for you, what are the benefits of this formalism. But just sort of for now, I just maybe would like you to accept that this is yes, you should look at this. You should take your favorite geometric setup, and you should look at this formalism and say, yes, I want this. I'm not going to do that for differential geometry. Okay. I should mention that sort of constructing six-functor formalisms is hard work. What one usually starts with is the star functoriality. So you have a functor, you have the star functors, usually some version of sheaves, and you want to construct all this other data. So think of the example of locally compact Hausdorff spaces, where these other functors, like these shriek functors, have something to do with proper support. So what one does is you assume that the category C comes equipped with two special classes of maps. You assume that there are open maps and proper maps. In specific examples, these do not necessarily have to be the natural maps that you might call open or proper. You can play around with this a lot. But the formal thing you require is that whenever you have a functor, whenever you have a map in the class of open maps, then the upper star functor has a left adjoint, and that's going to be the lower shriek. And whenever you have a map in this class of proper maps, then the upper star functor has a right adjoint. Well, we already knew that. That's the lower star. And you declare the lower shriek to be the same as the lower star. And now for a general map that's neither open or proper, what you demand is that there is some way to factorize an arbitrary map as an open map followed by a proper map. And then you define the lower shriek for that functor, for that map, as this composite for some factorization. And for all of this to work so that you can, the fact that like that with this setup, you can construct a six-functor formalism, that's hard work. Like I'm not going to explain to you how to do that. And you have to have some condition on how to do this factorization. So usually you require that maybe there's a contractible space of such factorizations. So in case that that you have this setup, note that since for a proper map, the lower shriek is the same as the lower star. In this case, the base change property that we had a few slides ago that we require for six-functor formalisms. Now, sort of, I don't know if is this visible, like in down below here? Yeah. So now this base change map involves the same adjunction. It involves the same functors. And in this case, there's actually a canonical map that goes from up right to right up. And if you give yourself a setup like this, one doesn't have to ask that there is a natural transformation between a natural equivalence between these two ways of going on the diagram. You are given a canonical map, and you only have to ask that this map is an equivalence. So in this case, you say that the Beck-Chavalit condition is satisfied for this pullback square, or you say that this diagram is vertically right adjointable. So this is the power of this construction theorem is like you ask for these two classes of maps. You ask that like the open maps have left adjoints, the proper maps have right adjoints, and you ask that certain maps that are canonically given to you are equivalences. So you only have to check some things. And the hard theorem is that in this case, you get all this data of a six-functor formalism. That's the magic of this construction. Okay. So now I want to move to the setting of differential geometry and sort of outline what exactly I want to do today. Oh, and if there's any questions at any point, please interrupt me. It's always hard if you're giving a Zoom talk, you're just sort of speaking into the void.
So can I ask a question about this square? So you started with two maps, F and G, and then you produce the squares. So how you can produce this square, or this square is given? So would you please explain?
Here it's a pullback square. So you're given the map from Z to W and the map from Y to W, and then this is a pullback square. So X is Z cross Y over W.
So this is a pullback with respect to which maps? Which maps or?
So this pullback takes place in the category C, so the category of geometric objects. So I'm gonna in the next slide, I'm gonna sort of pin that category down. But maybe for now, like assume that they're all topological spaces.
Yeah, okay, thank you.
Yeah. And then you hit this square with the functor D star, you get a square of categories. And there's a condition, this construction results, like asks that a certain natural transformation between these categories is an equivalence. Okay. So today I want to do this so now I want to sort of be in the specific setting where I take for the category C, I want to take the category of manifolds and smooth maps between them. And the six-functor formalism I want to construct is going to be something that like is going to be an analog of what in differential geometry would be quasi-coherent sheaves. So quasi-coherent sheaves are modules for the ring of functions on a ring space or a scheme. And so here the ring of functions is the ring of smooth functions of a manifold. And I want to do this in this sort of fully higher categorical setting. And so why do I want to do this? Well, I want to talk about some applications in representation theory of compact Lie groups. So if you're an algebraic geometer, you might know that one gets a lot of mileage out of viewing a category of representations of, say, an algebraic group as the category of quasi-coherent sheaves on the classifying stack of that group. So if G is your group, there's a stack called BG, and sheaves on this stack are exactly representations of the group G. And many properties of this category of representations can be deduced formally from the geometry of the stack BG. So now I want to do this not for an algebraic group, but for something like a compact Lie group. Okay. So how's this going to work? Well, in this setup of six-functor formalisms, we require that the category that we start with has finite limits. So we want to be able to take arbitrary intersections, right? So you can do this, for instance, in topological spaces. You can do this in a category of schemes. But in the category of manifolds, you cannot do this. So only so if you generically intersect manifolds, or well, generically it's going to work, but if you intersect two submanifolds in a third manifold in a way that's not transverse, the result will usually not be a smooth manifold. And so the solution to this problem is to work in a larger category where you think of manifolds, think of sort of differential geometry as embedded into algebraic geometry. So if you've never seen this notion, don't worry. Like for most of what I'm going to say is, well, you can forget what I said and just assume we're always working with manifolds and smooth functions. But I'll just say, like, there is a geometric formalism that extends the category of manifolds that looks very much like algebraic geometry. So there's topological spaces with sheaves of rings on them, but now the rings carry extra smooth structure. They sort of remember that you're they remember that, like, maybe something like the ring of smooth functions has a natural topology, and this is encoded in this ring. And so this category that I'm writing here is essentially contains all of the differential geometric objects that you can make by intersecting finite dimensional manifolds in a non-transverse way. And
so basically, excuse me, can I ask a question about this? So basically you have n space and kind of large functions like differentiable, and you consider simply finitely generated subalgebras, right? Basically.
I mean, no, you consider...
Yes. So basically, what else apart from finite? So suppose you have a large algebra commutative, and you consider finitely generated algebra, and you have a fine space, right?
So what kind of algebra did you say? A wedge algebra?
So when we look at your last line, right, you have kind of explanation, which actually it means this is a spec A, where A is a finite dimensional algebra.
Yeah.
Right. So basically, you have a CRN infinity large algebra that contains infinitely differentiable functions, and you consider simply finitely generated subalgebras. No, there are plenty of finitely generated subalgebras, but
I mean, you consider algebras that sort of admit, yeah, like, well, not so. I mean, they're not.
So you simply have a large algebra, and you consider all finitely generated subalgebra. It's also huge object, right? But what else you consider apart from that?
Okay, so there's
Simply to understand your definition, right?
so the definition is here. So the recall is maybe a bad word, but so what I'm telling you is that you can do differential geometry essentially the same way that you can do algebraic geometry, except you have to sort of change you have to change your notion of ring.
Mhm,
So in algebraic geometry, you work with say over like whatever, say over C, right? You work with a category of commutative algebras over C.
mhm.
If you want to do differential geometry over the reals, you have to remember that sort of you have to remember extra C infinity structure. So the category of rings in differential geometry is a category this is the category of C infinity rings or C infinity algebras. What this is you take Cartesian spaces. So you take which has the point, the line R2, R3, and smooth maps between them. So this is a category with finite products, and you just look at product preserving functors into sets or into the infinity category of spaces. So if you do this for not for Cartesian spaces and smooth maps, but for affine spaces and polynomial maps, then you just get back the usual category of algebras. But these rings, they have more structure. They're commutative rings over the reals, but they have a sort of extra functional calculus for smooth functions. And there's a theory that says that like you can take this category of rings or this infinity category of rings and do algebraic geometry with them. We'll talk about ring spaces and anything you want to do. And in this category, you can consider things like non-transverse intersections of manifolds. In the same way that, from in a usual algebraic geometry, you get sort of arbitrary schemes, finitely generated schemes, as by intersecting affine spaces.
So you're taking these algebras as your base category, and then you take the opposite category of that, like you do
That's
in
right.
algebraic geometry.
That's
Okay.
right. That's right. Yeah. So if you've never seen this before, feel free to black box this or forget what I said. Like for most of what I'm going to talk today, just think of manifolds and like a manifold with its ring of smooth functions. And this is so what I'm writing here, like there's a beautiful, interesting theory for these objects. But for today, this is just a convenient place to embed the category of manifolds in, such that I'm in the right setting to talk about six-functor formalisms. Okay. So I want to. These are all very good questions. So I have to. The construction of the six-functor formalism sort of depends very crucially on questions like this. So what does it mean what does it mean to do differential geometry as if you're doing algebraic geometry? What does it mean to sort of what extra structure do you need to have on your rings to talk about to have a good theory of quasi-coherent sheaves? That's sort of the questions that I want to address today. So I want to sort of say that the six-functor formalism, what it's going to be, is it's going to be sheaves of modules or modules for the ring of smooth functions. So now we have a question: what kind of modules do we use? Well, what you can do is like a ring of smooth functions, like that's just an ordinary commutative algebra of the reals, and so a category of modules for these, and there's a derived infinity category of modules for these. So you might say, okay, well, let's take that, but this will not work, and I'll explain to you why in the next. So the what we're going to need is some notion of modules that lives in a topologically enriched setting.
So all your modules are topological modules, right?
So they come with yeah, so they're enriched in topological vector spaces in some sense.
Okay.
But this is subtle, and this is what I'm going to address in like the next 5 to 10 minutes. So, so to get a six-functor formalism, like so, the main thing to prove is this. Sorry for going back. Is this proper base change theorem? It's sort of this property that sort of going up and right is the same as going right and up. And so now we want this for some version of modules for rings of smooth functions. So if you're just if you want to, here's a proof, more or less a proof that the usual notion of quasi-coherent sheaves for ordinary algebras that is a six-functor formalism. This satisfies this base change property. So what you have is say you have a like a pullback diagram of schemes. Well, that of affine schemes that corresponds to a push-out diagram of algebras, right? So D is going to be the tensor product of C and B over A, and hitting this with a functor that takes modules gives you this squared diagram. And now the question of base change is whether going up and right is the same as going right and up. But in this case, that's true. So say you start here with a C module M, and you go right, so you tensor to D, and then you go up. This means that you forget that you're a D module and just remember that you're a B module. So that's what's over here. Well, going up and right is well, yeah, so why is that the same as going up and right? Well, D was C tensor B over A. So here these C's drop out and you get M tensor B over A. And so that's the result of going right and going up and right. Right? So the basic problem, if you want to do this for in differential geometry, is that this fails to work for ordinary modules. So it is not true that the pullback of manifolds corresponds to the push out of commutative algebras. Actually, it corresponds to, so it doesn't correspond to this tensor product of commutative algebras, it corresponds to some kind of completed topological tensor product. So if here in this diagram you plug in for A, B, and C, you plug in these three algebras, this equation is going to fail because the tensor product here is going to be of a different nature than the tensor product here. And so this is why you need some notion of topological modules. So if what we want is some category of modules that themselves have like underlying topological vector spaces, so that we can take something like a completed topological tensor product, such that these tensor products will match. And in this case, we will have this base change property. Does that make sense? I hope it makes sense. All right. So how do we do this? Right, so to match these tensor products, we need some sort of topologically enhanced modules. Now this idea, now sort of this problem that we're now facing is where we have to sort of merge structures in functional analysis, something like complete topological vector spaces, like complete tensor products. Well, there's a lot of tensor products. There's injective, projective tensor products. We have to merge this with higher categorical methods. And sort of this is, historically, this is sort of a sort of fraught marriage. So let me explain to you what are the desiderata. What do we what is the setting that we want to work in? So we want to do higher category theory. So we need some category A that contains functional analytic objects, like space of smooth functions. So this is what's called a Fréchet space in functional analysis. And this needs to satisfy a bunch of conditions. Well, we want to do homological algebra. So we'd like this category A to be an abelian category, right? So we can make sense of chain complexes and homology. Also, like I told you a bunch of slides ago, we like to be in the setting of presentable higher categories. So we need this category A to be presentable. I'll say a few more words about what exactly this means in a second. So once you're presentable, there's very satisfactory ways to make sense of the derived category or the derived infinity category. So there's a natural subcategory of fiber and chain complexes that presents a very well behaved infinity category, and that's the setting that we want to be working in. And well, there needs to be this tensor product. There needs to be a completed tensor product on this category. And this tensor product needs to sort of interact well with the presentable structure, but what that means is that this tensor product needs to preserve colimits in both variables. So if that's the case, then you can form internal Hams for this tensor product. Otherwise, you cannot. So we need these three things. The problem is that sort of none of the classical categories that people consider in functional analysis, like the category of topological vector spaces, or the category of locally convex topological vector spaces, or the subcategory of Frechet spaces or Banach spaces, they do not satisfy any of these properties. So we have to come up with something. So how are we going to do this? Well, let me first let me say a bit more precisely what exactly a presentable category is. So a presentable category is a category that's large, where you can take all limits and colimits, but is still controlled by a small collection of objects. So what one usually does is you maybe start with some category of finitely presented objects, and then take formally filtered colimits, and you get the category of all objects, right? And another way to do this is, so a particular way to do this is what's called the P sigma construction. And this is something that you, even if you don't recognize it now, you have seen this in disguise many, many times. So what this P sigma construction do is it takes a small category that you understand very well, and it freely adjoins a class of colimits that are called sifted. And so this is sort of more or less how it works. What you have is some category of algebraic gadgets, maybe like commutative algebras or modules over a ring. And in there is the sort of the nicest, the class of nicest objects, the free and finally generated, or the finally generated and projective objects, in this case gadgets. And then the P sigma construction takes this very small class and produces the entire category gadget. And so the way this works is you take the category, this class of finally generated and projective objects, and you take functors into the infinity category of spaces, or the infinity category, or the category of sets that preserve products. So here's an example. So if you do this for the connective K modules, the infinity category of connective K modules in a commutative ring. So consider the finally generated projective K modules. Then this full category of connective K modules is the P sigma construction on this subcategory. And so that's what's happened if you look at functors that take values in spaces, and if you just look at functors that take values in sets, then you just get the ordinary category of K modules, which here is denoted by this little heart. It's the heart of the T structure. So this is a very powerful construction, and we're going to use this to produce the category A that we want. Right, so let me say a bit more about this particular example of modules. So in general, whenever you have a small abelian category and it has enough projectives, then it's incompletion. So where you formally add filter colimits, that's the nicest class of abelian categories. The Gottlieb abelian category, it has enough projectives, and you can take its derived infinity category. So you can take chain complexes of projective objects in non-negative degrees. And that derived infinity category is exactly going to be this P sigma construction on the projectives. And so this is just the same example from the previous slide. If you take for C to be the category of finally presented modules, then the int completion is the category of all modules. And there's the projectives that's just the subcategory of projective modules. And taking P sigma of this will give you back the category of all modules. And so this P sigma construction gives you a way to generalize away from abelian categories So it need not be the case for, so this p sigma construction is abelian whenever you put in an additive category. So it need not be the case that this category P was actually the category of projectives of some category of modules. Right? Whenever you put in an additive category P, the result is going to be abelian, and it's going to be presentable. So now the idea is to put in some category of projectives of like functional analytic nature to produce this category, to produce this nice category of quote unquote topological vector spaces. The idea is that we want to consider for our finally presented modules, we want to consider the category of Banach spaces. And so the derived infinity category is going to be the derived infinity category of the incompletion of Banach spaces. So now Banach spaces is not abelian, but it is additive. And so the subcategory of projectives is also going to be additive. So additive means that you have products and co-products, and they're the same. So you have sums. So then you have to ask, okay, what if you do this for category Banach spaces? What are the projective objects of Banach spaces? And this is a well-known functional analysis fact. This is a classical thing that people have figured out in the 60s. So consider the category of Banach spaces. And here I put a little kappa. So kappa is a cardinal that bounds how many Banach spaces we take. So if we put here a kappa, this means the category of Banach spaces that have a dense set of cardinality kappa. And so it turns out that this category has enough projectives. And the projectives are very simple to describe. They're exactly the spaces of absolutely summable sequences. So L1 is the space of absolutely summable sequences of the set of cardinality lambda. Now, the category that we want is just going to be sort of the idea is now just to take for the derived category of in Banach spaces is just to take this p sigma construction on the projectives of the category of Banach spaces. So we're going to do this. So it turns out that it suffices to only take Banach spaces that are separable for the smallest infinite cardinals. So Banach space, so that's separable in the usual sense. So there's a countable dense set. And in that case, the projectives in the category of Banach spaces, that's the category that contains all the finite dimensional vector spaces, 0, R, R2, and one extra object, the space of absolutely summable sequences of the natural numbers. And so the category that we're looking for, this good category of that has all the good properties, it's presentable, it has this tensor product, it's abelian. This category is this p sigma construction on this small category of projectives in Banach spaces. So it's going to be product preserving functors on this category that I denote here A. So if you were to take this category A and you were just to remove this one object, so you would just have all the finite dimensional vector spaces, then taking the p sigma construction would just give you back the category of R vector spaces. Right? So in vector spaces, all the finite dimensional ones are projective and finitely generated. And so taking p sigma of this will give you back all the vector spaces. But now we have this extra object that sort of controls all the functional analysis for us, which is L1 of the natural numbers, this projective Banach space.
In this category A, what are the morphisms?
So this is like the full subcategory of the category of Banach spaces on these objects. So the morphisms are continuous linear maps. Since we're in Banach spaces, they are the same as bounded linear maps.
Non-trivial thing is to understand how a finite dimensional copy of R maps into this L1, right, of N.
Well, so L1 is like, this is just a sequence space, so it's a countable sequence. And you require that it's absolutely summable. So if you take the absolute values of this sequence and you sum it, this needs to converge. And so all of the finite dimensional vector spaces, they sit in there by just taking 0 at some point.
Mhm.
Does that make sense?
Yep. Thank you.
So yeah, it is a fact that like actually you don't need all the finite dimensional spaces, you only need L1 because all the finite dimensional ones are retracts of the space L1. Okay. So by construction, by just category theoretic nonsense, this category that I'm gonna call aggregated vector spaces, that's a name that I'm gonna explain in a sec. It has all these good properties. So it's abelian, it's grothendieck abelian, it has enough projectives. And so immediately we can do homological algebra with this right away. There's an infinity categorical version, which is very easy to describe. So there you can describe it in various ways. So you can take the derived category, so you can take chain complexes of objects in this category. That's one way to do it. You can take the P sigma construction on this category A, but not in sets, but in spaces, and that will give you the connective part. And then if you stabilize, if you take spectrum objects, you get the full infinity category back. So this is very good. So this is the setting this is sort of the ambient categorical setting that we're going to put ourselves in. So I should claim that this also has a tensor product, so I should explain that to you. Yes. So okay. So this looks very abstract. This category is some category of functors from this guy into sets or spaces. So what is this? So if you have such a thing, you have a functor on this small category into sets. Well, it's product preserving. So you only need to know the value on R to know what its value on all the higher finite dimensional spaces is. So let's just declare that the value of f on R is some vector space V. That's just the name for this vector space. Well, with finite products, you cannot reach this object over here. So this is another, the value on L1 is not determined by the values on all these other ones. So I'm going to just denote the value of f on L1. I'm going to denote this by L infinity of V. Like in just like 3 seconds, it's going to become clear why I'm going to do this. So an aggregated vector space is sort of two pieces of data. It's this underlying vector space V, and then another vector space L infinity of V. So it's completely formal that this space as a set, that this set L f of L1 is the same as mapping L1 into F. That's just the Uneda, that's just Uneda's lemma. So you're mapping L1 into F, but like now imagine that F is actually something that you understand well, something like a Banach space. Well, it's a classical functional analysis fact that maps continuous maps or bounded maps from L1 into a Banach space. That will give you the set or the vector space of bounded sequences in that Banach space. So that's the set L infinity of the Banach space B. So that's the reason that I'm calling this L infinity of V. So L infinity means bounded sequences. Right? So this has to do with the duality between absolutely summable sequences and bounded sequences. The topological dual of L1 is L infinity. That's what's going on here. So you should think of an aggregated vector space as being a vector space together with a set of bounded sequences. So what are we doing here? Sort of instead of axiomatizing the notion of a vector space with a topology, as you would usually do in functional analysis, now we're going to axiomatize the notion of a vector space with a bounded sequence. And it turns out that this actually behaves much better categorically than topological vector spaces. That's like if you take away anything from this talk, let it be that. And so this vector space L infinity of V, this inherits a right action of the endomorphisms of L1. Right? That's if you have maps between, that's just the functoriality of F. That's just the fact that F is a functor, you get this action. And in fact, you only need this action. So it turns out that this category of aggregated vector spaces is exactly the same as endomorphism, as right modules for endomorphisms of L1. And it turns out that this is actually very simple to understand. So this is actually a very easy category. It's just right modules for some algebra, the algebra of endomorphisms of L1 in the category of Banach spaces. And this endomorphism algebra is very simple to understand. So this is maps from L1 to itself. So it's bounded sequences in absolutely summable sequences. So what is this? It is the set of infinite matrices, countably infinite square matrices, such that all of the rows are absolutely summable. And the sequence of sums is bounded. And if you impose these conditions, you can deduce that matrix multiplication of these infinite matrices, that's well defined, that converges. That's what these boundedness and summability conditions imply. So what is this category? It's just the category of right modules for the infinite matrix algebra, infinite square matrix algebra. And it turns out that sort of this solves all the problems that you encounter if you try to do homological algebra with topological vector spaces. Okay, so now let me explain to you why is this category symmetric monoidal. So first you can think of any you can embed or you can think of any topological vector space as such an aggregated vector space, right? Because what is an aggregated vector space? It's a vector space with a set of bounded sequences. Well, if you have a topology, you have a notion of bounded sequence, right? So there's a functor from topological vector spaces to this new category. And this is fully faithful on a very large, so here's a scary word that I don't want you to remember, but it's fully faithful on an enormous class of topological vector spaces. Unless you're some kind of weird functional analyst and your job is to come up with weird spaces, you will never sort of in nature come up with a space that is not sort of a class of spaces that is not fully faithfully embedded into this new category by this function. And so this category of aggregated vector space has a tensor product. So what you just do is, well, it's sort of in a precise way, this category is generated under colimits by these spaces L1, by the absolutely summable sequences. And so what you can do is you can just take the projective tensor product of Banach spaces. So this has this sort of defining property that L1 of S tensor L1 of T is L1 of S times T. And you can just declare that this is what the tensor product is on the generators, and then say it has to preserve colimits in both variables. That will give you a tensor product, and that's the tensor product we want. Now, this tensor product might in general be very hard to compute, but for certain spaces, like the ring of smooth functions on a manifold, it turns out that the tensor product behaves exactly as the other tensor products in functional analysis. So in functional analysis, there's a class of so-called nuclear spaces. So in functional analysis, like there's like Grothendieck in his doctoral thesis sort of proved that on locally convex spaces, there's sort of 12 natural tensor products, and sort of they all sit between the injective and the projective tensor product. And there's a natural class that Grothendieck introduced back in the day called nuclear spaces, for which all of these tensor products are the same. And if you're a nuclear space, then actually this sort of abstractly defined tensor product is the same as all of those. And that's fortunately the setting that we're going to be in, which is good. Okay. So now we have an ambient setting for the derived higher categorical setting where we can think, where we have like topologically enhanced modules with a good tensor product. And so that's where we can look for a six-functor formalism which has base change for manifolds. So the theory of smooth manifolds naturally embeds into this category. Right? So I can think of the ring of smooth functions. I can think of this as such an aggregated vector space. So I have to tell you what are the bounded sequences, and what you can just say is, well, a bounded sequence is a sequence that is pointwise bounded on the manifold. And this This gives you a functor from the category of Cartesian spaces into the category of commutative algebra objects of my aggregated vector spaces. And this functor now is going to have the crucial property that products of manifolds are going to be carried to tensor products of these algebras, because here the tensor products, recall from the previous slide, was this completed tensor product. And so here's something about these C-infinity algebras that if you don't know, you can ignore. But sort of this embeds the theory of manifolds fully faithfully into the theory of algebras in this functional analytic setting. And now this discrepancy of these tensor products that I had on the slide back, this sort of fundamental problem that the tensor product of modules is not the same as the tensor product of algebras, this is now fixed. So the six-functor formalism, what it now does is it takes a manifold that sort of lives in this sort of, here is where rings of smooth functions live. Think of them as an algebra, as a commutative algebra in this functional analytic setting, and then take modules for that object. Right? So this sends an algebra A to aggregated modules for the associated aggregated commutative algebra. And now, because these tensor products are the same, we indeed have that push-out diagrams are going to be carried to right jointable squares. So this is very promising. This is, you know, the hardest part of the six-functor formalism is now is taken care of. So this is not quite a six-functor formalism. I will skip to what the six-functor formalism actually is. So it turns out that sort of to also satisfy the other conditions that this construction is supposed to have, what you have to do is you have to sheafify this functor. So this functor on the previous slide, that's not a sheaf. If you sheafify it, then it becomes a six-functor formalism. So this is the theorem. The sheafification of this functor that takes modules for these functional analytic rings, that's what I'm going to call quasi-coherent sheaves. And the theorem is that indeed this is a six-functor formalism for the classes of open embeddings and proper maps. So you can check indeed that this functor QCO now sort of satisfies this base change property for proper maps and also for open maps. And you also have to prove that any map of manifolds can be factored as an open map followed by a proper map, but that's a technicality I don't want to get into. Okay, there's a bunch of slides here that I have about how to actually prove this. I'm going to skip these and just move on to the applications, which have to do with representation theory. So, so we have this sheaf called QCO, so quasi-coherent sheaves in differential geometry. Now what I want to do is as an algebraic geometry, I want to evaluate this sheaf, I want to evaluate this functor on something like the classifying stack of a group, something of the form BG. So BG is not a manifold, but it lives in the category of sheaves on manifolds. So I have to extend the functor QCO to the category of sheaves on manifolds. So here again, there's this sort of infinity category of these infinity rings. Just imagine that here we put manifolds, right? If that's more conducive to understanding. And so maybe this is something very familiar from algebraic geometry. The QCO itself is a sheaf of categories. So it becomes a functor on the category of all sheaves by this formula. This is just a right-con extension. And the six-functor formalism also extends, but now one has to be careful that not all the maps between stacks have shrieks. Only certain maps of stacks have shrieks. But in particular, all representable maps of stacks have shrieks. And since we're going to work with stacks of the form BG and maps between them, those are all representable, so those will have shrieks. So in that setting, everything is fine. So now some applications to representation theory. So I can now just tell you what the category the category of representations of a Lie group or a Lie groupoid is. So a Lie group is a Lie groupoid is a groupoid object in the category of manifolds. So G0 and G1 are manifolds. And its quotient G0 modulo G1, that's a stack. That's a stack in the world of smooth geometry. And since QCO is now a functor that takes in such objects, I can just evaluate QCO on this stack. And that's by definition the category of representations of this groupoid. So you can work out what this is. So by definition, QCO of this quotient stack is the limit of this diagram of categories. If instead of a groupoid you pick a group, this is somewhat simpler to understand. So if you have a group, then the ring of smooth functions is a commutative Hopf algebra as an object in this category of commutative algebra objects in aggregated vector spaces. So this is this, if you have an algebraic group, its ring of regular functions is a Hopf algebra in the category of commutative rings. And so the same is true here. So now this is sort of the showcases that sort of with this categorical setup, we can just do differential geometry as if we were doing algebraic geometry. And you can show that in the case, the category of G representations for this group is the same as comodules for this Hopf algebra. And these are quite familiar. So these contain familiar things. So what does it mean? So say you give yourself some functional analytic space, say you give yourself a Fauché space, a comodule structure is just a map, right? It's a map from V to smooth function on G tensor with V. So that's the same as smooth functions on G with values in V. And such a map from V to smooth functions on G with values in V, that's adjoint to a map from G times V into V. And so this is just a G representation. But now the fact that it comes from a map like this means that it's not just a map of sets. It means that this map is actually smooth for the natural for the manifold structure on G and the natural infinite dimensional manifold structure on V. So this category of G representations contains all of these this is a what we've constructed here is a category of G representations that has all the good properties that people in that algebraic geometers and category theories want. It's presentable, it's stable, but it contains lots of interesting functional analytic data. And the six-functor formalism gives you lots of interesting functorialities. So in this case, for a group, so BG is this quotient. So G0 is a point modulo G. So BG is the quotient of a point by the group. You have the canonical atlas, the canonical map from point to BG, and this induces the Schrieg lower star functor. That's which is the right adjoint to the upper star functor. But now because we have a six-functor formalism, there's also a lower Schrieg functor. And these functors are different. So what this one does is this is just the functor, this is just the induced representation. So it sends like a vector space V, it sends this functor sends this vector space to smooth functions on G, a smooth function on G with values in V. But this one does something different. This sends it to smooth functions, not smooth functions, but compactly supported smooth functions on G with values in V. So automatically, the six-functor formalism gives you the functor of compact induction. And not only that, it tells you that there's this intricate system of functorialities associated to these functors. So I think I should wrap this up in a couple of seconds. So there's some cool applications that I haven't mentioned yet. So the nice sort of let me just very briefly flash for you the real upshots of this formalism. What you can show with this formalism is that this category of representations for a group has very strong dualizability properties in certain higher categories of vector spaces. So according to the cobordism hypothesis, giving a highly dualizable object in some n category is the same as giving a fully extended topological quantum field theory that takes the point to that object. And with this formalism, you can show that these categories of G representations that I just construct for you actually have these strong dualizability properties. That just follows from the geometry of these classifying stacks. Should I flash this? No, I will just. Yeah, if you want to know about that, you can ask me. I think we'll stop here.
Thank you very much for your very nice talk. I think we should give an applause in many ways. And are there any questions? Then just in the audience, just unmute yourself and ask it straight away. I have one question. Oh, sorry. Go ahead, Severin.
Okay, so I was wondering, could you explain again? At some point, you talk about these derived affine something which are finitely generated. So
Yes.
can you say again, finitely generated as what and over what?
So in this category, so here we have this again, this P sigma construction. So this category of rings, it's the sort of the rings of smooth functions on Cartesian spaces take the role of the polynomial rings in usual algebraic geometry. So in this world, an algebra is finite, like a C-infinity algebra is finally generated if there's a surjective map from a ring of smooth functions on like some Rn to your algebra. So you have n generators, but sort of in the C-infinity sense. And you have a surjective map. That's just what it means to be finally generated. And sort of dually if you apply the spectrum functor, if you go to the world of geometry, then being finally generated means exactly that you can be embedded into some that there is a closed immersion into some Cartesian space. So this just means that sort of we're not working with infinite dimensional manifolds. So
yeah, okay.
Yeah.
Okay, thanks.
So like this is sort of analogous to like in topology, like a six-functor formalism is defined on locally compact Hausdorff spaces. And so locally compact means in particular like not infinite dimensional. And that's essentially the same role that this is playing here.
Okay, thanks.
Any more questions? Well, I had a quick one. So you mentioned these coherent sheaves on classifying stacks, which is basically representation theory. I mean, algebraic geometry, very often you also look at equivariant sheaves. So you have a quasi-coherent sheaves on a quotient stack, let's say, and you get quite a lot of nice results. It's Lunds-Bernstein, Bernstein machinery. And can you get something analog here in this more general setting?
Well, what was the well, I wouldn't say the setting is more general. Like it's just genuinely just like a sort of like these settings sort of intersect only sort of on like finite groups or something. But so what were the results that you were talking about? Like
So I mean, very often you want to have a theory of G equivariant sheaves, let's say for algebraic groups or group schemes, and on a certain condition you can develop that, and then you have nice notions of cohomology also, and it's like Lunds-Bernstein, for example. There's this very classical theory. And basically, these are coherent sheaves or quasi-coherent sheaves on classifying on quotient stacks for a variety with group action. And I was wondering if you have an equivariant picture here also in this setting.
Yeah, so the equivariant picture is yes. So the equivariant picture is actually that's sort of was already in the talk. So like this equivariant setting is actually this sort of this Lie groupoid setting. So if you put here like so if you have an action of say you have a group G that acts on a manifold M, like then here you would put this would be the action groupoid.
Yeah.
Right. So here you put M and here you would put G cross M. And the two maps would be the action and the projection.
Right.
And so this already encodes this that example. So since sort of this is all, like it's sort of in principle, like this category is very big, and it's sort of the virtue of this is that sort of even with sort of infinite dimensional functional analytic objects, you still have a lot of sort of categorical control. But of course, a lot many results, many classical things in algebraic geometry will not carry over.
And very often you also would like to have some kind of decompositions of categories of quasi-coherent sheaves on some variety and into smaller pieces. I mean, and I was wondering if this machinery might help you to actually get more conceptual decomposition theorems also in this respect.
I mean, in principle, yeah, sort of in principle, that's what I would claim that sort of this is the right setting to look for theorems like that, but sort of specific applications are going to depend, of course, on like actually doing some hard analytic work. So if you say you care about like, I don't know, quasi-coherent sheaves on B of S1, so representations of S1 or of U1. Well, there's like, of course, there's sort of a beautiful representation theory of infinite dimensional, like there's Peter Weil and sort of these these all imply interesting results about these categories of quasi-coherent sheaves, but sort of, yeah, like sort of these sorts of results, like, okay, what are the generators, like what kind of, what kind of semi-orthogonal decompositions do you have? Sort of these sorts of theorems are all going to have to come from like the sort of like this is going to be sort of hard analysis work.
Okay, thank you. Do we have more questions or comments from the audience?
Yes, thank you very much for the nice talk. And I was curious if you can clarify a little bit when you said like Morita categories, like what do you mean?
Yeah, so I like this is so you mean here, I assume this.
Yes, exactly. Yeah.
Yes. So so these are the sort of this slide is sort of the impetus for a lot for this project. In physics, in quantum field theory, or in particular, like in this field of sort of of topological quantum field theory, you look at functors from Bordism categories or higher Bordism categories to some linear target, some category of vector spaces. And the question is sort of if you go higher, if you go into the setting of n categories, the question is what should you put there as some category of higher vector spaces? And so sort of as experience has shown, one very good such category is this higher Morita category. So what is this category? Its objects are, so in this case, its objects are En algebras in the category of presentable categories enriched in aggregated modules. And so sort of that's the object. So the objects are En algebras. Then the one morphisms are bimodules between En algebras. And these bimodules themselves have to be En minus one algebras. And then the two morphisms are En minus two algebras in bimodules. And then the three morphisms are En minus three algebras in bimodules, etc. You go all the way down until you come to bimodule maps and then also natural transformations because you're working with categories. So this is sort of a higher version of the usual Morita category where you have algebras and bimodules as morphisms. And here you have En algebras, so algebras for the little n disk operad, and bimodules as morphisms that are themselves En minus one algebras and so on.
Thank you very much. Yeah.